Well, it's a great honor to be part of these celebrations, and it's really a pleasure to hold this laudatio in honor of Søren, Galatius, and Oscar Randal-Williams, whose mathematical development I have been privileged really to watch unfold, what I might say from the front row. I really can't think of anyone in my field, at least, who is more deserving of the Clay Research Award, and I think my task is to explain why I think so in the next 15 minutes or so. So I'm going to be mixing some readings and some explanations on the board, but let me first say a little bit about the awardees. So Søren Galatius grew up in town of Randers in Denmark, from where he went to close by University of Aarhus and eventually became a student of Ib Madsen. At the time, I was collaborating with Ib Madsen, but soon Søren joined us and work progressed rather more speedily. Having received his doctorate, he moved then to Stanford as Sego assistant professor. He received tenure after only 2 years and was later promoted to full professor, returning to Denmark in 2016, this time Copenhagen, where actually Ib Madsen had moved and there was a flourishing topology group. The Clay Foundation previously honored him with the Clay Research Award. He received a silver medal from the Royal Danish Academy of Sciences and was elected a foreign member of the Academy while he was at Stanford. He also received the Elite Research Prize from the Danish government and a Consolidator grant from the ERC. Let me move on. Oscar Randal-Williams spent his school years with his family as an expat in Spain, from where he went to Oxford as a undergraduate and became my student in 2006. Still in his first year, and having solved a problem that I had given him, clearly far too easy, I suggested to read and generalize the paper by Søren, and a year or two later, their collaboration started in earnest while Oscar was still a graduate student. After 2 years as postdoc in Copenhagen, he came back to England on a Herschel Smith postdoctoral fellowship and is now full professor there. For his work, he has received the LMS Whitehead Prize, the Livium Research Prize, as well as international prizes such as the Heinemann and the Oberwolfach Prize. And presently, he holds an ERC starting grant. So let me now come to the core of their joint work. They completed a major program that has seen extraordinary and unexpected advances for higher manifold theory. In a trilogy of papers comprising some 250 papers and appeared in ACTA, JAMS, and Annals, they established an analog of the so-called Mumford conjecture, now Madsen-Weiss theorem, for manifolds of even dimension, thus computing stable homology of moduli spaces for manifolds in these dimensions. Their work has invigorated geometric topology and has already seen beautiful and far-reaching applications, many by a group of impressive young scholars who have been inspired by their work. And I list a few of them. It includes Küpper, Hebestreit, Kranich, Palmer, Schreinebrunner, Bonatus, Daimler, Raptis, and many more. Really, I should say, they're picking up on a tradition that started in the 50s with Tom, Milner, Cavere, Smale, Novikov, many of whom received Fields Medal in the 60s and 70s. So let me go a little bit more into detail what I actually want, what the work is about. So I think really it's what I would call the algebraic topology of manifolds. Manifolds are one of the most important objects in geometry, maybe even in physics and mathematics more generally. So we take W, a smooth manifold, and the diffeomorphism group, when you study one object, you want to understand its automorphisms. And we tend to have I want to consider the boundary fixed by the diffeomorphisms. Now, B of diff is a classifying space, but really one way to think about it is just a way of thinking of a modelized space of these topological manifolds, and that can make that more precise in a moment. And so the cohomology of B diff is actually containing all the characteristic classes of manifold bundles. So in dimension 2, these become very familiar objects. WG is an oriented surface of genus G, and we know all such oriented surfaces are all of this form, and we also know what the unoriented surfaces look like. So we have a complete classification. The diffeomorphism groups are interesting. They're very closely related also to a discrete group, the so-called mapping class group, studied a lot in geometric group theory. And their B-diff, what I already called the modelized space, in the case of surfaces in dimension 2, this is actually very closely related to the modelized space of Riemann surface, known from algebraic geometry. And so the cohomology in this case of B-diff is just the same as the cohomology of the mapping class group, and also the cohomology rationally of the modelized space of Riemann surfaces. So there's very familiar things in this dimension. In higher dimensions, these notions are somewhat different. Nevertheless, let me now state what Søren and Oscar proved. So we take WG1, sort of the higher dimensional generalization of a genus G surface, namely instead of taking S1 cross S1 connected sum, so torus connected sum G times, we take Sn cross Sn G times connected sum, and let that be our WG. But we're not, of course, in higher dimensions. These are not the only manifolds. There are many, and the first theorem starts with just taking not visible. It's starting by taking W, just being any closed n-1 connected manifold of dimension 2n. And then we can sort of connect sum this starting manifold W with these higher dimensional genus G surfaces. And look at the limit as G, as I add more and more such Sn cross Ns. And indeed, the homology of B diff of these things are completely known, the sort of the limit of these. Namely, they are expressed in this term on the right-hand side, omega infinity mt theta to n, indicating really that it is completely independent of W I started off with. MT is actually a Thom spectrum, and omega MT is therefore well known for algebraic topologists and can be computed completely. So the right-hand side we have a very good handle on and can be computed. Now, there is actually a more general statement, I call it theorem 1 dash, where I don't have to start with an n-1 connected manifold, but actually just any simply connected manifold. And a theorem can be proved, or they proved a theorem, I should say, for all n, where the answer, the omega infinity mt theta, is actually only dependent on the n-1 skeleton of the manifold I start off with. So again, what we have here is a complete computation of these modularized spaces, the homology of these modularized spaces, topological modularized spaces, something that there's no such statement, had no such statement been qualitatively known before. Completely revolutionizes that part of the theorem. Now, the second part of their work, and that of course is also important, if you're interested in any one manifold, then you might like to understand how this one manifold relates to the manifold when I increase the genus. And indeed, they proved that we have homology stability, meaning that the cohomology of these B diffs is independent of G for the degree relatively low to the genus chosen. So in particular, this means we have a complete computation, for example, of these the B diffs of the higher dimensional analogues of the genus G surfaces, and the answer is actually just written there. And the PI are, well, they stand for pointer eigenclasses and are directly related to them. Okay, so this letter, the theorem 1 I mentioned was true in any dimension, and so in particular, actually, that theorem, I want to point out, includes the Madsen-Weiss theorem, and is therefore a generalization of that. Madsen and Weiss proved that theorem in dimension 2, and there's a slightly different name also for the theta 2 in this case. The statement about homology stability in dimension 2 was previously known by Hara, who proved homology stability for the mapping class group, and therefore, combining those two things, it had been proved by Madsen and Weiss, or it follows from their theorem that we have the Mumford conjecture in those dimensions completely computed the rational cohomology stably for the moduli space of Riemann surfaces. So having now said that this is an analog of the Mumford conjecture, it is far from true that this is an easy generalization. The theorems are an easy generalization. Quite the opposite. It seemed crucial in dimension 2 that one studies all surfaces at once, and that one also has a complete classification of two-dimensional manifolds. Now, nothing is closer to be true than that complete classification in higher dimensions, and so it seemed to be really quite out of reach. It also seemed very lucky that, and a coincidence that the diffeomorphism groups in dimension 2 are very closely related to the mapping class group, namely homotopy equivalent in higher dimension, for higher genus. And again, Hara had proved this for the homology stability for mapping class group only. So in their solution, Galatius and Randal-Williams first deconstructed and reorganized the proof of the Madsen-Weiss theorem, and then developed parametrized surgery theory and proved the first homology stability theorem for diffeomorphism groups. So this one down here. So let me just say very briefly what where the proof maybe might have been motivated and what I needed to do. So we had a theorem that actually looked at the cobordism category in dimension n-1 with objects d-1 dimensional manifolds, and the classifying space of the cobordism category had exactly this omega infinity MT spectrum in the answer. And a way of understanding this classifying space of the cobordism category is actually as the space, the moduli space of d-dimensional manifolds with certain theta structures. But this is really all you have to take all such manifolds. And the answer, if you go back here, you have to cut it down to those manifolds that you might want to look at, namely these W connected sum WGs. And that is actually exactly where the surgery, the parameterized surgery, had to come in. So, for example, in this statement, in this theorem here, when we consider all manifolds, in particular, it also contains disconnected manifolds, and you really have to come to connected ones. And so the theory that had to be developed was quite substantial. Okay, so the results of a completely fresh view and philosophy on higher dimensional manifolds and the diffeomorphism groups. In the 70s and 80s, smoothing theory led to pseudo-isotopy theory, where a manifold is stabilized by thickening. So let me go to the next slide. So the thickening is done by crossing by an interval, which in turn, through a work of Waldhausen, could be studied by algebraic case theory. Now, manifolds are stabilized by connected sums, namely Sn cross Sn. So we stay in the same dimension, and now can be studied by this cobordism series, the MT spectra, which is much easier to compute than K-theory. So it is a very different approach to what had been done really in the 80s. And indeed, I think progress had been relatively slow, while we now have these wonderful computations. Okay. Right. So in addition to these many explicit homology computations that we now have, there have been a number of very surprising applications of the main result. So let me just list a few. Michael Weiss made spectacular use of the results to disprove a conjecture in the triviality of topological Pontryagin classes, which he had previously spent some 18 years trying to prove. In a completely different direction, Hebestreit and Steimle are using an algebraic formulation of parameterized surgery theory to prove foundational results in Grothendieck-Witt theory, now part also of a 9-author paper. Randal-Williams with Botvinnik and Ebert has used the results to show that the space of metrics with positive scalar curvature have a rich topology, something that the connected components of which was actually had interested Hitchen some 30, 40 years ago, and very little was actually known about the spaces themselves, and they show actually that it's very rich topology. And then another thing I want to mention is a very imaginative application by Küppers, who proved that the homology and the homotopy groups of the classifying space of the topological group of diffeomorphisms of a disk. So diffeomorphism of a disk were very hard already. And what he proved only a few years ago was that these homology and homotopy have actually they're finitely generated in each degree. So I've written it down here. And the reason why this is, why Oscar and Søren's theorem is of importance is this fiber sequence. Let me just explain that very briefly. In the middle, you have B diff W. So this is the diffeomorphisms of W. On the right-hand side, you have embeddings of W into itself. And you fix just something, some subspace of the manifold, here denoted by delta minus, and you fix the complement when you embed. That's delta plus. And that is the space on the right-hand side, while the fiber of this is actually the B diff of the manifold M, so the other part of the boundary crossing interval. Now that's a very important, it turns out to be a fiber sequence, but it's important in the sense that we can tackle, in principle, the right-hand side by the embedding calculus of Weiss and Goodwillie, while the middle part, you see, you can use any W really, and so in particular our WG, and make G infinite, where we understand everything now by Søren and Oscar's theorem. And so therefore we can tackle really what is on the right-hand side, and in particular when M is itself just a disk. And so Kupers was able to study B diff of the disk from this sequence. This fiber sequence was previously also used by Weiss in his work on the Pontryagin classes. Right. So most recently, Galatius and Randal-Williams have also built on Weiss's work here and established the independence of the Pontryagin classes, which is actually a topic that Oscar will talk about later this week. This latter work by Kupers is very ingenious and forms at the beginning of a recent deep investigation into homotopy type of diffeomorphism groups of spheres and disks by Randal-Williams and Kupers in even dimension and Randal-Williams and Kranich in odd dimensions. Using also work of Watanabe and Weiss, this has led them to compute huge parts of their rational homotopic groups, completely dwarfing the results that had been known so far. Randal-Williams' talk in the ICM gives a good survey. He also puts forward a conjecture that completely describes their rational homotopy theory. So it's surprising how little we actually know even about diffeomorphisms of a disk. Now, coming to my last slide here. Homology stability was, of course, a part of, sort of the two theorems. The second theorem, if you want to get information of the B diffs of any specific manifold, then you have to have homology stability. Now, this already played an important part in the Matzen-Weiss theorem, of course, and the topic of homology stability, which traces its origin really back to Borel and Quillen and K-theory, has grown into a sub-subject with much progress and good work. This led a few years ago, Galatius, Randal-Williams, and Kupers to completely rethink the approach to homology stability for topological spaces. At the heart of homology stability statements are generally some kind of homotopy commutativity, some sort of En structure with n greater than 2 in terms of higher algebra. They come up with the idea of a cellular resolution for these algebras. Having developed this higher homotopical algebra, they also immediately show the strengths of their apparatus by finding important applications to mapping class groups, proving secondary stability, and general linear groups, solving, among other, long-standing problems of conjectures by Suslin and Rockness in K-theory, going back 30 years and more. This work develops in three-part, again, a highly complex new theory drawing on techniques from algebra, geometry, homotopy theory, and then they apply this to concrete questions by means of complex and intricate computations. So I just written here very briefly, what do we mean by secondary stability? Well, you can measure how badly stability fails, how different these homology groups are. But the difference between these groups in themselves show stability. So let me finish by just saying I feel extremely fortunate to have been a collaborator of Søren, proud to count Oscar among my students, and entirely privileged and lucky to have been part of a development that has seen algebraic topology of manifolds unstuck, and the mathematics of our heroes from the past come to new lights. Thank you for listening, and many congratulations to Søren and Oscar.